Okay, are you guys able to see my screen? Can you guys see my screen? I opened a slide called probability theory for inference.
Yes, sir.
Okay, so we're going to be looking at probability theory for inference today. So let's dive into it. So the first thing we need to be familiar with is something called discrete random variables. So a random variable can have a set of different values. For example, a random variable can be weather with the values sunny, rain, cloudy, snow. Similarly, it can be a Boolean random variable containing the values true and false. And here are some notations for probability. We are pretty much already familiar with these, but just a quick review that if weather is equal to sunny, we can directly write sunny like this. And for probability for weather equals to sunny, sometimes you can write like this. Probability of sunny equals 0.725. And for cavity equals true, we can write it just cavity, and cavity equals to false, we can write it not cavity. Once I'm just trying to join, set that. All right. The next slide talks about some probability axioms. Axioms, if I'm asking this correctly. So there are three axiomations, which are basically theories of probability. The first theory tells you that any kind of probability should be within 0 and 1. It can be less, it can be greater or equal to 0 and less or equal to 1. So it can be a fractional value, it can be exactly 0, or it can be a 1. And if P of true is equal to 1, then P of false should equal to 0. And lastly, P of A or B should equal to P of A plus P of B minus P of A and B. So this symbol is called or P of A or B, and the last symbol, this is called and P of A and B. We'll see more examples on these to make it clear. Let's look at this example. Um, okay, there's also a few rules for calculating conditional probability, and there's a product rule. So for conditional probability, uh, if we're trying to calculate probability of A given that B is true, then the equation should be probability of A and B divided by probability of B. And probability of B here is known as normalization constant. We'll be diving more about these a little later. First, this is the same rule. We'll be using this rule a lot. Probability of x comma y is probability of x and y. So it's basically this rule right here, conditional probability. Probability of x given y is equal to true, probability of x and y divided by probability of y. And the product rule is if you only multiply x given y times probability of y. So both are pretty much the same rule. The first one is called the conditional probability rule, and the second one is called the product rule. Let's look at an example. Let's try to calculate these values by ourselves. Again, if you have any questions, feel free to interrupt. So, in this table, what can we see? We see that the probability of burglary and alarm is 0.09, and the probability of burglar and not alarm is 0.01. That means the case where a burglary happened and the alarm rang, the probability of that case is 0.09, and the case where a burglary happened but the alarm didn't ring, the probability of that case is 0.01. And similarly, the alarm rang but a burglary didn't happen. The probability for that is zero point 0.1, and the alarm didn't ring and no burglary happened. The probability for that is zero point 0.8. So now, if we want to calculate these values, how can we do that? Let's start with the very bottom. Let's try to calculate the probability of alarm. Now, to calculate the probability of alarm only, um, we have to look at all the probabilities of uh, all the probabilities where alarm is true. So for burglary equals to true, alarm is true for 0.09, and also for burglary equals to false, alarm is true for zero point 0.1. So we have to add them up. This entire column. For this entire column, the alarm is true. So the probability of alarm is going to be 0.09 plus zero point 0.1. That should equal to 0.19. Are you clear about that? So in case probability of not alarm should be if you add these two up, 0.81. But we don't have to find that in this case. So let's go to the next one. So this one is saying we have to figure out the probability of burglary and alarm. So it's given directly in the table. So burglary and alarm, that's 0.09. Probability of burglary and alarm, 0.09. And this symbol represents probability of burglary while alarm is true. This is where we're going to need the rule for conditional probability. The product rule to be more precise. So we're trying to figure out the probability of burglary given alarm is true. So given alarm. Now, if we look at this rule, conditional probability, we see the probability of A given B is true should equal to probability of A and B divided by probability of B. So here my A is burglary and B is alarm. The first thing I need to do is calculate probability of burglary and alarm. So we did that in the previous step. probability of burglary and alarm that equals to 0.09, or we could see it directly in the table. Burglary and alarm is 0.09. And we have to divide that by probability of B, which is probability of alarm. So divided by probability of alarm, which we calculated at the very first step, 0.19. Now, if I plug that in my calculator, 0.09 divided by 0.19, I get the value 0.4736. So let's write it 0.474. And lastly, we have to calculate the probability of alarm given burglary is true. Probability of alarm. So can anybody tell me what should be the answer? The only difference between this one and the previous one is the A and B's are shifted now. So again, we have to look for probability of A and B, which is again this value, alarm and burglary, 0.09. And then we have to divide it by the probability of burglary. So to calculate the probability of burglary, what do we have to do? Which two numbers should we add to calculate the probability of burglary?
0.09 plus 0.01.
0.09 plus 0.01. So now if I put that in my calculator, it's going to give me 0.9. So let's verify our answers with the next slide. So our probability of alarm should be 0.19, which we got. And our probability of burglary and alarm should be 0.0. We got it right. And the probability of burglary given alarm is true, is this one, is 0.47. We got it right. And the last one is probability of alarm given burglary is true, it's 0.9. So we have that as well. So do we understand if a table like this is given, how we can calculate different probabilities and conditional probabilities? Let's look at a different example. In this case, a table won't be given, but a scenario will be. So let's try to figure this problem out. It says a person is put in. Do you guys have any questions regarding this problem first? Then we'll move on. It's fairly simple. You just have to use the formulas. The formulas are given right here. So if you do face any problems later on, you can reach out. So right now, let's move on since we have a lot to cover. So if a given scenario is a person is put in front of a jury. The jury finds the defendant guilty in 98% of the cases in which the defendant has committed a crime. So in 98% the defendant is found guilty in 98% cases in which the defendant committed a crime, and it finds the defendant not guilty in 97% cases in which the defendant has not committed a crime. Now, from that, what can we infer? Okay, there's one final line. Furthermore, only 0.008 of the entire population has committed a crime. Okay, let's start with the last line. It says that only 0.88 of the entire population has committed a crime. That means the probability of being a criminal is 0.008. Probability of criminal is 0.008. Now, this can tell us another thing, that that means probability of the person not being a criminal should be 1 minus 0.008, which is, I think, 992.992. Is that clear? The probabilities should always add up to 1. So if the probability of criminal is 0.008, then the probability of not criminal should be 1 minus 0.008. So now let's look at the other facts. It says the jury finds the defendant guilty in 98% times if the defendant has committed a crime. So that means the probability of being guilty given that the person committed a crime. That means the person is a criminal. The probability of guilty given person is a criminal equals to 98%. That's 0.98. Now, similarly, we can find the probability of not guilty given the person is criminal. That's going to be 1 minus 0.98, which will be 0.02. Are you guys following along? Somebody confused about anything? You can ask. And our last condition is the defendant is found not guilty 97% cases where the defendant has not committed a crime. So not guilty, not committed a crime. Probability of not guilty and not committed a crime, so it's not a criminal, equals to 0.97. So the probability of guilty given uh, not a criminal should be 1 minus 0.97. One minus 0.97 equals to 0.03. So this is all the information we can gather up from the given scenario. Now, what do we have to figure out? Our question is, if a random person is found guilty by the jury, what's more likely, criminal or not? That means this time it's given that the person is found guilty. So guilty is true. We have to figure out if uh, what's the probability of being a criminal and what's the probability of not being a criminal, and which one is higher. Is the question clear?
Yes.
put it in terms to find out is the probability of the person being a criminal given that the jury found them guilty. True. We have to find out the probability of the person being a criminal while guilty is true. And also the probability of the person being a, not being a criminal if found guilty. We have to find both and measure which one is greater. So now how can we do that? Our available information is here. Let's look at the rules again. If we use the um, computing conditional probability rule, can we get somewhere? We have to figure this one out. So using the conditional probability rule, we can say that the probability of the person being a criminal and given found guilty should be, if criminal is A and guilty is B, it should be the probability of criminal and guilty. However, we don't have that value. We don't know in this given scenario, we don't have anywhere probability of guilty and criminal. In this case, can we go for a different rule? Do we know of a different? There's something called the Bayesian rule, which tells us that the probability of A given B should equal to probability of B given A times probability of A divided by probability of B. Can we use this rule? So if my A is criminal and B is guilty, my probability of B given A should be probability of guilty given criminal. Just this value right here. So let's copy that. To multiply it with probability of A, so probability of criminal in this case, and divided by probability of guilty. Since B here is guilty. Now we have the values for this one and the probability of criminal. However, we don't have the value for probability of guilty. Now, since we have to figure out both the values, we can write the same. We can follow the same formula for this one as well. The probability of the person not being a criminal but found guilty. In this case, what's going to happen is I have to look at if A is not criminal and B is guilty, then it should be probability of guilty given not criminal, which is this one right here. And we have to multiply it by probability of A. In this case, it's probability of not criminal. So we have that here. and divided by probability of B, which is again probability of guilty, just like the previous one. So if we have the equations, the first one and the second one, and let's say this is our equation 1 and this is our equation 2. If we divide equation 1 by equation 2, now the only unknown thing on the right sides are the probability of guilty. So if we divide these two equations, we can omit the probability of guilty since we don't know the exact value of probability of guilty. That way we can find a ratio between our two desired values. Do we understand the approach? So if we divide the first equation by the second equation, we're going to get something like this. It should be this divided this to the left side divided by the left side, and the right side divided by the right side. But in this case, the probability of guilty will be omitted because the both sides have probability of guilty. It should be probability of guilty. This portion divided by this portion. So is everybody clear how we came to this point? If you have any questions, please ask. Okay, now we can just plug in the values since everything on the right side is known to us. So the probability of guilty given criminal, that is 0.98, 0.98 times the probability of criminal, that's 0.008, divided the probability of guilty given not criminal, which is this value right here, guilty given not criminal, point zero 0.03 times the probability of not criminal, which is 0.992. So let's put this in the calculator and let's see what we get. 0.98 times 0.008 divided by 0.03 times 0.992. So we get something like 0.263. Now, what does that tell us? If that tells us that the probability of criminal given guilty is true divided by probability of criminal, the probability of not criminal given guilty is true is 0.263. So in this case, can we infer which one is the larger? The probability of criminal given guilty or the probability of not criminal given guilty? If we're dividing two values and we get an answer less than 1, what can we infer? What can we conclude from that? Which value is greater? the the value on the top or the value at the bottom. To get a clearer picture, let's divide 2 by 3 first. The answer to that should be 0.667. And if we divide 3 by 2, that should be 1.5. So if we divide two numbers and get an answer less than 1, we can ensure that the bottom value is greater than the top value. And if we get the answer which is greater than 1, we can ensure that the top value is greater. So in this case, since this is less than 1, which is less than 1, so we can ensure that not criminal is greater than criminal. So the probability of, let's just copy that. So there you go. That's your answer. So the chances of the person being not criminal is higher. So our question was, if a random person is found guilty by the jury, what's more likely? So our answer should be not criminal. And in the next slide, this is pretty much given to you. So you can look at that as well. But if you understood everything, it's basically the same thing, what I did. They're using these. So this is the equation we used, the Bayesian rule, and they approached in a very similar way. They they got to equations and they get the conclusions. So are you guys clear about that? If you have any questions, you can ask, or we'll move on. All right, let's look at a few more examples. That way, we'll have a clearer picture. So in this example, it's saying that college students were asked if they cheated, they ever cheated on an exam. The results were broken down by gender, and this is what we got. If a student is a male and they cheated, the probability of that is 0.32, and probability of a male not cheating is 0.22. So in these tables, you have to keep in mind that this it should always add up to 1. For example, the probability of cheating and not cheating in total for male and female. For the person cheated, if you add up the cheating equals to yes. If you add up both the probabilities, you should get 0.60. And if you add up cheating equals to no for male and female, you should get 0.40. And if you add those two up for cheated, yes and no, you should always get 1. The same thing applies for male and female. If you add the probabilities of male, cheated or not, you get 0.54. And if you do the same thing for female, you get 0.46. And if you add those two up, those should also add up to 1. So the question here is, given that a person has cheated, what is the probability he is a male? So what we have to figure out is the probability of male given cheater equals true. So for this, we can use the conditional probability rule, male and cheater, which is this value right here, male and cheated yes, 0.32, divided by probability of cheater. So if you want to figure out the probability of cheater, you simply have to add these values up. So cheater equals yes for male and female. You get 0.60. So if you divide 0.32 divided by 0.60, you get your answer. So there are a few more examples given in the slides. This time the table is given if the person is left-handed or the right-handed, and if a person is male or female. So it's very similar to the one we just did. So we have to figure out the probability of the person being a man, given that the person is right-handed. So in the first case, we have to figure out the probability of M or male given R or right-handed. So again, it's the probability of M and R divided by the probability of R. So if you look at the table, you'll find your values. The second one is fairly similar as well. Third one is also pretty similar. Let's look at the third one. We have to find out if we have to find out the probability of a person being a female given that she is left-handed. So it should be the probability of F given L. So what should be my probability of F, which is the stands for female, should be 0.45 plus 0.06, which is 0.51. However, the rule says that we have to figure out the probability of F and L, which is this value here, and divide that by the probability of L, which is this value. So it should be 0.65 divided by 0.14. So, 65, 0.06. The probability of female and left-handed should be 0.06, and the probability of left-handed, if we add these two values, we're going to get 0.14. So that's what this slide is doing as well. Now, the differences in the last question are the events being a female and being left-handed independent. How can we determine if an event is independent? If two events are independent of each other? To, to find that out, we have to figure out the probability. In this case, we're trying to figure out if F and L are independent. If L is independent of L, if F is independent of L, we can determine that by calculating the values F, the probability of F given L, and the probability of F. So if the probability of F given L is equal to probability of F, that means F does not depend on L. It's an independent. It's an independent uh, event. So if we calculate these two values, we see that they are not equal. So that means they are not independent. They are actually dependent on each other. So again, to determine if two events are dependent on each other, first we have to do is calculate the probability of the first one given the second one, and and then we have to calculate the probability of the first one alone. That means the probability of F given L, if that is equal to the probability of F, that means L doesn't matter when we're calculating the probability of F. But in this case, it did matter because the values are not the same. We'll learn more about independence in an upcoming example. We have to cover a lot, so I'll move on. So there's another example given in the slide, which is pretty similar. Cavity and toothache. I'm guessing you guys can figure this one out by yourselves. It's the same rule. There's nothing new here. We basically have to use these two rules. And there's another example given for three different variables. So this time there's toothache, which stands for T, cavity stands for C, and X-ray, which stands for X. So in this cases, if we want to figure out the probability of cavity or toothache, what we have to do is look at all the values where cavity is true and look at all the values where toothache is true. So for cavity, it should be this entire row here, point 108, point 012, point 072, point 008. You have to add all that up. And for toothache, it should be these four cells. So we already added these two up. So the new ones are only point 016 and point 064. So if we add one, two, three, all these six values, we're going to get the probability of cavity or toothache. Similarly, if we want to calculate the probability of cavity alone, we just have to add these four values. So everywhere cavity is true, we just add the probabilities. So in this case, we have to figure out the probability of not cavity given toothache is true. So if we use the conditional probability formula, it should be the probability of not cavity and probability of toothache divided by the probability of toothache. So a not cavity and toothache. Let's find that. Not cavity is the bottom row and toothache is the first two columns. So these two values, 0.016 and 0.064. If we add those two up, we're going to get the probability of not cavity and toothache. And we have to divide it by the probability of toothache, which is basically these four cells. So again, it is pretty much using the same rules, but in this case, since there are three variables, the table is a bit different, but the logic is pretty much the same. Similarly, there are more examples given. I'm pretty sure if you understood so far, these shouldn't be too difficult for you. So we can pretty much calculate this using the formula as well, and also this. And it's saying here that these two probabilities should sum up to one. Um, the probability of cavity given toothache and the probability of not cavity given toothache, which we pretty much use that logic to calculate in this portion. Do you remember the probability of guilty given criminal? That was given to 0.98. So we were sure that the probability of not criminal given, sorry, the probability of not guilty given criminal, it should be 1 minus 0.98. So these two values should always add up to 1. Probability of guilty given criminal and the probability of not guilty criminal. So we pretty much already used these concepts. So now comes independence. What independence means is that let's say we're trying to calculate the cavity, probability of cavity, depending on toothache and catch. However, we're introducing a random variable called weather. Now, weather is completely irrelevant for calculating cavity. In this case, it's saying that if weather has four possible values, we have to redraw this table here four times. And this table contains 8 values. So 8 times 4, that's 32 entries together. And weather doesn't even matter in most cases. So if we can identify an independent variable, so weather here is independent of toothache or catch and cavity, the other three variables. So if we can identify an independent variable, we can neglect that or omit that to reduce our data size. Because working with 32 entries would be much more difficult than working with these 8 entries. These 8 entries would give us would be more efficient and will provide us with a result in much less time than working with 32 entries. So if we get the chance, we should always identify an independent variable. Now, there's something called conditional independence. First, let's look at the independent variable again. If A and B are completely independent, then the probability of A should equal to the probability of A given probability of B. We saw that here. So these two values should be equal because in this case L didn't matter. So in this case B shouldn't matter to A and A shouldn't matter to B. The probability of B should equal to probability of B given A. So given A or not given A is the same thing for B. So in these cases we can identify them as independent. And if we're trying to figure out if they're conditionally independent, it should follow this rule that the probability of A and B given C should equal the probability of A given C times probability of B given C. Now, if we break down this equation a little more, you get something like this. You can assume that A and B is X, so the probability of X given C, that should equal to the conditional probability formula, the probability of X and C divided by the probability of C, and X and C. If you replace X with A and B, you'll get this, and if you uh, put probability of C on the right side, you get this. So it's simple mathematics. If you're confused a little, I suggest just grab a piece of paper and work this out. And the next slide talks about the Bayesian rule. We already saw this. We already used this rule. So there's nothing new here. There's some more examples. We already covered that. So if we're trying to determine if A and B are conditionally independent given C, we have to make sure these three conditions are true. The last one we just saw, and also we have to prove these two conditions. Probability of A given B, comma C. Probability of A given B and C should equal to probability of A given C. We'll look at a few examples. In this case, it says that the probability of toothache, cavity, and catch. If I have a cavity, the probability that the prob catches, it doesn't depend on whether I have toothache. So saying the probability of catch doesn't depend on toothache. So, but you have given that you have cavity. So the probability of catch given toothache, comma, cavity, if that equals to the probability of catch given cavity. So the toothache doesn't matter here. And similarly, if the toothache doesn't matter, we can do that for negative cavity as well. And if we can determine these two things, that catch, the probability of catch depends on only the cavity, then we can determine this equation here. So what we're doing here is the first condition, A given B, comma C, if that's A given C. So if toothache doesn't depend on it, if we are not dependent on toothache, we can simply omit that and check the values are equal. If they are, then we can come to this conclusion. Similarly, if a catch doesn't depend on toothache, we can come to this conclusion. And finally, if we can prove this, the very last statement, then we can rest assured that T and X, which is toothache and the catch in this case, are conditionally independent of C. So what conditional independence, why is it important is because if we use the formula for joint probability, we'll have to calculate 7 independent entries. But using conditional independence, we have to calculate 5 independent. So in most cases, what uh, conditional independence does is distribute, um, it reduces an exponential n to a linear n. Now, this was a very small example. We went down from 7 to 5, but in a big data set, that can be hugely advantageous for us. We'll actually look into another slide today to clarify this a bit more. It's called the naive bias. The probability slide is pretty much done here. So let's jump to the naive bias. Don't have much time, but we have to cover that today. So the naive bias classifier. But if you have any questions up till now, you can ask, or I'll move on. With the naive bias, first, just some background information there is pretty simple stuff. I expect you to read that, and I expect you to understand this. But if you do face any issues, you can reach out to me later on. This is basically saying that first we have to determine an algorithm, and then we have to train our model, things like that. So a naive bias classifier is one of the ways to do it, and it works pretty well, surprisingly. So what the um, there's some again some basic probability theories, and there's also an example which is very similar to the one we did on this one, criminal and guilty. So let's quickly look at this in case maybe if you face confusions later on. I'll quickly explain this. So it's saying that the HIV global probability is 0.008, and in this case, test and HIV positive. These are the two variables here. So if test is the probability of test while HIV is positive is 95%. The probability of test being positive given HIV is positive, and the probability of not test, that means test equals negative, given HIV is negative, is also 95%. So from a first test, the result is positive. What's the probability of having HIV? So again, we have to calculate the probability of HIV given test. So if we use the bias rule again, we'll get something like this. And for not HIV given test, if we use the bias rule, we get something like this. So this value is greater. This value is 6.5 times greater than that. So the probability of not HIV is greater. Um, there's another example with slightly altered value, but it's basically the same thing. In that case, the probability of not HIV is also greater. Now let's look at an example, like how can we use the naive bias classifier. Um, let's say this is our training data set. It says the temperature. It has two attributes, saying that consider the event A represents a good day to play tennis, and its opposite event represents not a good day to play. So play tennis, this is considered A, yes and no, and event B, therefore, if it's a warm day, it's assumed that the temperature is above 50 degrees Fahrenheit. So if uh, temperature is considered warm if it's above 50, and if it's below 50, it's considered as cold. So what's the probability of A? That means the probability of uh, lateness equals yes. So there are one, two, three, four, five, six, seven entries, and among them there are three yeses. So the probability of A should be 3 divided by 7. So what's the probability of B given A? So when we say the probability of B, we're assuming that here warm is yes and cold is no. So the probability of B, that means the probability of B being warm given A equals yes. So in all the three cases where A is equal to yes, the first row, this row, and this row, the temperature is above 50. The first one is 70, the second one is 75, and the last one is also 75. So that's a direct one. So the probability of temperature being warm given the lateness is yes is 1, because in every case it is warm. Basically 3 divided by 3, which is 1. And the probability of B, so we take all the values and how many are there where temperature is equal to warm. 1, 2, 3, 4, 5. So it's 5 divided by 7. Now, if we apply the Bayes theorem here for calculating probability of A given B, so it's the probability of A and B. So these two values here. Oh, I'm sorry. We're using the bias rule. Let's look at the bias rule one more time. So the probability of B given A times probability of A divided by probability of B. So B given A is 1 times probability of A, which is 3 by 7, divided by probability of 5 by 7. So simply applying that rule, we get the probability of A given B is 0.6. Now, that was a fairly simple example with one teacher and one label. But in the real world, story with that example, there are going to be other attributes who win humidity temperature. Now, in this, if we try to determine, let's say we want to determine A given B and C and D. Now this can get pretty difficult while using the bias rule. To calculate this, we have to figure out the probability of A and also the probability of B and C and D given A. So if there are a lot of features or attributes, using the bias rule would make it almost impossible. That's what it's saying, that it's not even computing that is impossible. So this is where the naive bias classifier comes in. What the naive bias classifier does is assumes that all the events are conditionally independent. We read about that, conditionally independent. What that will do is, instead of calculating this entire thing, we can simply replace this with this value here. If you look at the slide, it will be a bit clearer to you. Uh, what were the conditions? Uh, this condition practically right here. Conditionally independent. See them side by side to get a better picture. So if we look at this condition, if there are two attributes, A and B, so it should be A given C times B given C. So if there are multiple attributes, we can simply write B given A. In this case, it's the attributes are B, C, D, and the condition given is A. So we should write B given A times C given A times D given A. So it doesn't matter how many attributes you have, all you have to do is break them down into separate, uh, conditionally independent entities. So we're basically using this condition, this equation. So the problem with naive bias is it trades accuracy for simplicity. The accurate thing to do would be to actually use the bias rule to calculate this very difficult to calculate thing. But since it's very difficult to calculate, the naive bias classifier says that to make it a bit more simple and to make things more workable, since in the real world there will be a lot of attributes and things are going to get very complicated, we assume that the attributes are conditionally independent and we use this formula instead. This is not very difficult to calculate. So it trades accuracy. It loses a bit of accuracy, but in return, makes the uh, it makes it makes the task much more simplistic. So let's look at an example. Yeah, okay, let's look at this example. In this case, this table is given. There are four attributes: the outlook, temperature, humidity, and wind. And our label is, or the decision we have to make is play tennis, yes or no. So if we look at outlook first, and if we try to calculate the probability of outlook equals sunny, given that play tennis is yes, we get 2 by 9. How do we get 2 by 9? We scroll down a little bit more. We see that play tennis yes equals 9 by 14, and play equals no. The probability of play equals no is 5 by 14. That means there are 14 entities here, 14 rows, and 9 of them are yes, and 5 of them are no. So where does this 2 come from? So if we look at the table where play is equal to yes, so play tennis is equal to yes, we get these 9 rows which are marked in red. So among them, you can see 2 of them are sunny. and the others are either overcast or rain. So among nine, two of them are sunny. That's why the probability is 2 divided by 9. Similarly, for overcast, uh, given play is equal to yes, that means we have to work with these 9 rows, and among those 9 rows, there are 4 outcasts. So it's 4 by 9. Similarly, for no, there are, if you're trying to calculate the probability of outcast given play equals no, we have to look at the 5 no's and check which how many of them have outcasts. Oops. In this case, we see that none of them have outcasts, so that's 0 divided by 5. Similarly, we can calculate all these values, and after that, if we want to see the naive bias in action, based on the values we calculated so far, we can come to these decisions that the probability of outlook equals to sunny given that play equals to yes is 9 by 2, which we just saw in this table right here, 9 by 2, while the probability of outlook equals sunny given that play equals yes, that's 9 by 2. So what we're trying to do is, given a new instance, predict its labels. The instance is given that the outlook equals to sunny, temperature equals cool, humidity equals high, and wind equals strong. So the values we calculated here in these tables, if we apply those values, temperature equals cool and play equals yes, simply have to map those. Temperature equals cool and play equals yes, that's 3 by 9. That's where we got the 3 by 9. And similarly, temperature equals cool, play equals no, that's 1 by 5. If we plug in all these values, we can use the naive bias rule. Uh, this portion, if you remember the rule, it's simply taking all the attributes for given yes and multiply them all together. So we're multiplying the probability of sunny given yes, the probability of temperature equals cool given yes. So all these values, and we get something like this, 0.0053. And if we do this for no, which means we have to multiply all the values on this side, we get something like 0.0206. So since the probability of no is greater, we can assume that this given instance, our prediction is latent is equals no. Do you understand how this works? I went through this a little bit faster since we were running out of time, but it's fairly simple. I think if you take a little time and go through this one more time, I'm pretty sure you'll understand it. There's nothing too complicated here. But if you do have any confusions so far, you can ask. There's one more final example given. This is basically the same HIV problem. However, in this case, we'll try to use the naive bias, and in the scenario says that we're taking multiple tests. In the first test, we got a positive, and we took another test and got that positive as well. So, what is the probability of having HIV? So, this time we took 2 tests. So, there should be T1 and T2. So, if we use the naive bias approach, the probability of HIV given T1 and T2, both of them are true. We use the naive bias rule. We get the probability of T1 given HIV, the probability of T2 given HIV times the probability of HIV. So if we plug in the values, we get something like this. And for non-HIV, it's basically the same equation. Plug in the values, we get something like this. So we see that in if the both test results are true, the probability of having HIV is actually higher than probability of not having HIV. It's actually 2.9 times. So in this case, our answer should be the probability of HIV is higher. And finally, there's an algorithm given. We'll be skipping this for this semester since we're covering a lot and we still have a lot to cover. And this can be a bit too complicated for you guys in this short time. We still have 3 chapters to cover. So I'll, I already talked with the other instructors about skipping the algorithm and they agreed. So up to the HIV example. This is where we'll stop. You can ignore the remaining slides. All right. So any questions regarding today's class? We talked about probability, conditional probability, joint probability, point distinction, independence, conditional independence, bias rule, negative bias. We talked about a lot of different topics today, but none of them were, I hope, not too difficult. And we also looked at a lot of examples. So I would suggest you to go through the slides. I'll be giving you the slides very soon. As soon as this recording is complete, I'll be giving you both the recording and the slide. So if you do face any confusions, I would suggest to watch the recording again and look at the slide side by side. And if you still have confusions, you can always reach out to me anytime you want.
So, is there any probability of having another quiz before final?
Yeah, the probability for that is 1. So you will have another quiz pretty soon. Actually, we have a meeting tonight with all the instructors, and I'll also be giving you an assignment. So I talked to Ipshitapu. She told me to take another quiz and give you an assignment. So we will be having a quiz hopefully this week or the next week, since the next week is probably the last week. I'll notify you once we're sure. I think we have to talk with other sections and finalize a date. So hopefully I'll let you know in a few days about the quiz date and the syllabus and everything. And I'll be posting an assignment in a few days as well. All right. We already had one quiz for this course, right? I wasn't there when the quiz took place. I think if Shita put up it. It was in box, if I'm not mistaken. There was MCQs. Is that correct? So as far as I know, there were MCQs, and it was in box. I think we'll go for a similar approach for the second quiz as well. But again, it'll be decided after the meeting tonight. So we're pretty much almost out of time. Let's stop the recording here.